Okay, so once again, good evening to you all. My name is Barry Griffiths, and I teach mathematics at the University of Central Florida. And we're going to do a few things this evening. We're going to talk about the subject of mathematics and how broad it is, how it is almost a world in itself. Then I'm going to talk about places around the world that mathematics has taken me and could take you as well in the future, I hope. And then to finish, we're going to do some fun mathematics related to an area of math that I really enjoy myself. So I know that a lot of you guys are in middle school, and so you will start with something like Algebra 1. And then what do you take after Algebra 1? It's geometry, right? So you take geometry, okay, and then what comes next? Algebra 2, is it? See, I didn't grow up in the American school system, so I'm guessing a little bit based on my son's experience. And then after Algebra 2, is it pre-calculus?
I think it's trigonometry.
Pre-calculus and trigonometry. The sort of parallel subjects. Okay. And then what? Then you get to calculus, right? So a lot of you will know that you go through this list of subjects to pretty much finish your K through 12 education. So most of you, you're all good at mathematics, I'm sure, will probably take calculus in the final grades of your schooling. Okay, but then you get to college, and I assume that that's your goal. And so really you tend to start with calculus when you get to college. You start with calculus 1, and then it's pretty easy to predict what comes next. It is calculus 2. So you see a trend here, because what is next is calculus 3. Well, then you may not know what comes next because there is no calculus 4. So does anyone know what class you take after calculus 1, 2, and 3? It is several years in your future, so maybe you wouldn't know. But after that, you take a class called differential equations, which sounds really complicated, but once you've taken calculus, it is a natural progression to taking differential equations, which are just equations. They've got equal signs in, and they've also got derivatives, and you learn about derivatives when you take calculus. Okay, once you get through all of these classes, well, the engineering majors think that that's the end of math. But the reality is that's really where math begins, okay? So you take these classes here, and then you enter the world of mathematics. It's at that point that the good stuff begins. And the world of mathematics is really, really broad. Let me give you a sense of how broad it is. Because every 10 years, they come up with a document, and it is called the MSc. And the MSc stands for Mathematics Subject Classification. So I'm sharing my screen. Can you see it? Is there a document on the page? This is the very latest edition of the MSc. It's MSc 2020. And you can Google it if you want to see it in its entirety. But I should warn you, it's 151 pages long. It's incredibly detailed. And so on the first page, they have all the broad topics of mathematics. And they have codes, as you can see, going from 00 up to 97. Now, you probably didn't know that there were that many areas of mathematics, but the truth is there's a lot more. These are just the introductory titles to all the branches of mathematics. So if I scroll down, it gets a little bit scary, I must say, but each of the topics in mathematics has subtopics. And so you might say, well, what do mathematicians do? Well, what they do is they study some of these areas of mathematics. And so you might think, well, will you ever run out of areas to study? And the answer is no, because there are thousands and thousands of them. So I'm already on page 9, but we've gone through hundreds and hundreds of different areas of mathematics already. And the one I'm going to talk about a little bit, I think, starts on page 12. There it is. So we're going to do some number theory at the end of my talk, because that's the class that I'm teaching right now at UCF. I'm teaching a class in number theory, which is branch number 11 in the MSc. But you can look through this at your leisure by going to Google. But this thing is enormous. It just goes on and on and on forever. And it just goes to show you that mathematics is so much more wide-ranging than you can possibly imagine when you're in middle school or even high school. It's a massive topic. And that's why at UCF, there are 50 professors, and at all the other universities, they'll have a similar number. So that's why there are thousands of mathematicians in the world, is because they're all studying different areas of mathematics. And so I'm not going to dwell on them anymore. It can get somewhat overwhelming, but I want to show you that there are so many areas of mathematics. So the next thing I want to talk about, let me go back to me again. And because I'm going to talk about myself for a few minutes. Because as you can probably tell from my accent, I did not grow up in Florida. I grew up in the UK. And if you want to know what it's like in the UK, just step outside tomorrow morning, and that will give you a very good indication, because it is cold. So when I was 19 years old, a bit older than you guys, but I was 19 years old, I had never been abroad. I'd never been outside of the UK. I had never been on a plane. And so I was at university in the UK, and I decided to apply to be an exchange student. And an exchange student goes to another country and studies there. And so I applied to go to the University of Texas in Austin when I was 19. Thankfully, I was accepted. And so I flew out there, and this was August of 1994. So before you guys were born. Now, you can only imagine the culture shock that I faced when I went from the UK to Austin, Texas. For a start, it was a lot hotter than anything I'd ever experienced. In the UK, 70 degrees is considered hot, okay? When I got to Austin, Texas, it was 95 degrees. I'd never experienced anything like it. So I got to my new place where I was staying, this apartment, and I was really tired because I'd just flown all the way from England. And because I was tired, I just wanted to sleep. But the problem was there was a noise in the background. And I like to sleep when it's nice and quiet. And there was this noise in the background. Do you know what the noise was? It was something I'd never heard before. It was air conditioning. So anyway, I thought, you know what? I'm going to sleep a lot better if I turn that noise off. So this was my first big mistake when I got to Texas, is I turned off the air conditioning, thinking I would sleep better. Well, you can imagine what happened, okay? I woke up half an hour later and I was sweating like crazy because the room was so hot. So I had to get up, I had to shower and change the bed sheets because I'd sweated so much. It was so hot. And so this is the kind of silliness that you do when you go abroad for the first time. So eventually, well, it didn't take long for me to stop making silly mistakes and to learn to live with the air conditioning and to get used to being in Austin, Texas. But it was an amazing experience. I learned so much. I grew up as a person, I matured, and I decided I wanted to come back to this country for graduate school. And so I applied to the University of Florida in Gainesville, and I was accepted. And so I was in Gainesville for a couple of years, and then I graduated. And then eventually I got the job at UCF in 2002. And I've been there at UCF ever since. So almost 20 years now, I've been teaching mathematics at UCF. But it all started with me being an exchange student. And so one of the things I do now that I'm a teacher at UCF is I set up exchange programs. So if you come to UCF when you're older, or even if you don't, you can go to any school, they will have exchange programs. So here's some of the exchange programs that I have set up. Let's see if I can put them on the screen for you. I'm very bad with Zoom, I must confess. So there's one of them. This is the first exchange program that I set up, and naturally it's in England. So students can do what I did, but in reverse. They can go from the USA over to England and study. And this has been a very popular program. In fact, I'm sending a student next week. He is going from UCF over to Surrey, and he's going to be there until June, and he's really excited to go. So that was the first one that I set up. The next one, let's see, like I say, I'm very bad with Zoom. Maybe I have to stop sharing and do it this way. Okay, so here's another one. So I set up an exchange program at RMIT. RMIT is the Royal Melbourne Institute of Technology in Melbourne, Australia. So there's another really cool place that you can go if you study at UCF, but I'm sure at many other places as well. The third place I set up an exchange program was in Spain at the University of Cantabria, because we have a lot of Spanish speakers at UCF. And so it is natural that I set up a program there. And then the next one I set up is very special to me because, let's see if you can see it, because this is where I work in the summer. So I work at UCF in the fall and in the spring, but then every summer I go over to Italy and I teach calculus and I teach differential equations. And I don't have an office over there because I'm only there for a few weeks. And so I hold my office hours on the balcony that you can see in the picture there. So I regard that as my office. And that bridge that you can see in the background, I think is 800 years old. So if I look one way over the balcony, I see that bridge. And then if I turn my head and look the other way, I can literally see the Vatican, where the Pope lives. And so there's history all around me when I'm in my Italian office, when I'm on the balcony there. So if students come to me and ask me questions, that's great. But if they don't, it's also great because I can just look at the scenery and it's really, really amazing. There is one other exchange program that I've set up, and I did that last semester, and it is in India. So I don't know if any of you have Indian heritage, but by the time you come to UCF, certainly it's going to start this year, students will have the opportunity to study in India and vice versa. We're going to have Indian students coming to UCF. So all in all, I've set up 5 programs in England, in Spain, in Australia, in Italy, and in India. So this is typical, actually. It doesn't matter where you go to college. I recommend that you look at what study abroad options you have available to you, because it really can change your life. That's how I came to this country when I was 19 years old. And needless to say, I'm a little bit older than 19 now. So it completely changed my life being an exchange student. And so I recommend it to you all. Right. Let us get to the fun stuff. Let us do some mathematics. So you've seen enough of me. Let's go to the board. So I have a question for you guys, first of all. What do you think is the most famous theorem in mathematics? I suspect you will have heard of it, most of you. Armin, you got your hand raised. What do you think?
Quadratic.
The quadratic formula is very famous, but it's not really regarded as a theorem. And so someone's actually given me the right answer in chat. It is the Pythagorean theorem. So here's a question. Who came up with Pythagoras' theorem? It's a trick question. Yes, the answer is Pythagoras, right? Hence the name. So you'd be surprised. Some theorems don't get named after the person who came up with it. So Pythagoras' theorem. Is it a recent thing? Or does it go back a few years? It goes back a lot of years, actually. It goes back, I believe, over 2,500 years. So it's an ancient result. So what does it say? Does anyone know? What's Pythagoras' theorem? Anyone know? The Warners have got their hand up. What do you think, Mr. Warner?
A squared times b squared. Wait, a squared plus b squared equals c squared.
A squared plus b squared equals c squared. And what are we talking about here? What are A, B, and C? It is, you are right. And someone just said they are the lengths of the sides of a triangle. So any old triangle, A, B, C, A squared plus B squared is C squared. Is that true? What do we think? No, that's not quite right. So Erica and Kai have said, no, it's got to be a right triangle. Okay, so it's got to be a triangle with a right angle in it. Okay, so A squared plus B squared is C squared. Is that now right? What do we think? No, still wrong. What's wrong now? Or A squared plus B squared, C squared, right triangle. What could go wrong? Okay. C has to be the hypotenuse. All right. So Pythagoras' theorem says that when you have a right triangle and C is the hypotenuse and A and B are the lengths of the other two sides, then A squared plus B squared is C squared. So that is Pythagoras' theorem. Okay. So the first person to prove that was Pythagoras. It turns out that there are over 360 different proofs of Pythagoras' theorem. I always think it'd make a great calendar, right? You could look at a proof of Pythagoras' theorem every single day of the year. That's fantastic. Except I'd be the only person who would buy that calendar, so it wouldn't sell very well. Anyway, I'm going to show you one of the proofs of Pythagoras' theorem. And this one was derived by a man called James Garfield. Now, has anyone ever heard of a man called James Garfield? Why is he famous? I'll give you a clue. It has nothing to do with mathematics. Anyone ever heard of James Garfield? No. He was not on TV because they hadn't invented TVs then. Anyone else? James Garfield. Yes, Mohid. He was a president. He was the president of the United States. And actually, he's most famous for being one of the 3 assassinated presidents, along with Abraham Lincoln and John F. Kennedy. So James Garfield was assassinated, unfortunately. But before that, he came up with a proof of Pythagoras' theorem. So let me show you what President Garfield did to prove Pythagoras' theorem. It's a very interesting proof. So he started with a right triangle, no surprise, and he called the sides A, B, and C. And then what he did is he extended this length here by an amount equal to A. So if this is A, then this is A. And then President Garfield created another right angle, and he went across by an amount equal to B. So this is B. And then he joined up these 2 vertices, and he put a line there, and he said, well, these 2 triangles are congruent. And so if this is A and B, then the hypotenuse must be C because they're congruent triangles. Now, question for you. This whole shape here on the outside, it's drawn fairly accurately. It's not supposed to be a rectangle. Does anyone know what this shape is here on the outside? I'll give you a clue. It begins with T. Have you ever seen such a shape? You might not have. I'll give you a few seconds to have a think. It is, yes, a couple of you have just said it is a trapezoid. Now, I don't have a lot of space here. Normally I'm working on a big board, so hopefully I've got enough room. But the area of the trapezoid, I don't know if you're familiar, but there's a formula for the area of a trapezoid, and it is 1/2 times the sum of the parallel sides, and the parallel sides are the top and the bottom. So if we add them, we get A plus B. So it's 1/2 times the sum of the parallel sides times the height. And you can see that the height is A plus B as well. So the area of the trapezoid is equal to that. Now, I think it should be obvious that the area of the trapezoid is the same as the area of the 3 triangles, because we've got 1, 2, 3 triangles here. So I think it's obvious that the area of the trapezoid is the sum of the area of the 3 triangles. Now, you should definitely know what the area of a triangle is, because it's 1/2 base times height. So if you look at triangle number 1, its area will be 1/2 base times height, so 1/2 A times B. And if we look at triangle number 2, well, it's the same triangle because they're congruent. So it has the same area, which is 1/2 A times B. And then finally, if we look at triangle number 3, well, this is a right triangle as well. And so its area is going to be 1/2 base times height, which is 1/2 of C squared. So this area has to be equal to that area. So to finish this off, I need a little bit more room. So we've just determined that the area of the trapezoid is this, and the area of the 3 triangles is this, and they have to be the same. So now what I'm going to do, and you should have seen this before, I suspect, is I'm going to multiply A times B by A times B, sometimes called the foiling formula or the distribution formula. And what you get is A squared plus 2AB plus B squared. You use that formula every 10 minutes, it seems, in mathematics. It's a very common formula that gets used. Now, on the right-hand side, we've got a half of AB plus a half of AB. Well, a half plus a half is 1. So we get 1 times AB plus a half of C squared. Well, now, if I distribute again on the left-hand side, I get a half of A squared plus AB plus a half of B squared is AB plus a half of C squared. Well, at this point, you see that the ABs cancel. And if we double both sides, we get that A squared plus B squared is C squared, and President Garfield had proven Pythagoras' theorem. So that's really an amazing way to prove Pythagoras' theorem. It's actually much simpler than the proof that Pythagoras came up with himself. So that's a really neat result. So anyway, we knew that this was true, right? We knew Pythagoras' theorem. So the next question I have for you is, do you know any whole numbers that satisfy Pythagoras' theorem? So I'll give you a few seconds to ponder on that. So Adhip has said 3, 4, and 5. And that's correct because 3 squared plus 4 squared is 5 squared. 9 plus 16 is 25. So 3, 4, and 5 is said to be a Pythagorean triple because it's 3 numbers that satisfy Pythagoras' theorem. Okay, do you know any other Pythagorean triples? Adhip has said 6, 8, and 10. Now, that's a good choice because 36 plus 64 is 100. However, mathematicians don't like this one simply because all you've done there is doubled the numbers. And so we like this 3, 4, and 5 because we say it's a primitive Pythagorean triple, whereas this one just doubled the numbers. 6, 8, and 10 have a common factor of 2. So although 6, 8, and 10 is a Pythagorean triple, it's not a primitive Pythagorean triple. So we like this one better because it's primitive. 3, 4, and 5 have nothing in common. Can you think of another primitive Pythagorean triple? You might not. It's not obvious. Armand said 9, 12, and 15. That is true, but again, it's not primitive because 9, 12, and 15 have a common factor of 3. Now, Adhip has just come up with a second one because he said that 5 squared plus 12 squared is 13 squared. And that is correct because this is 25, this is 144, and they add to 169, which is 13 squared. So here we have a primitive Pythagorean triple because 5, 12, and 13 don't have any common divisors. There's no number that divides into those numbers other than 1. Now, Erica and Kai have got a third one, which is 8, 15, and 17. That's a really good one. It's true, first of all, because 64 plus 225 is 289, which is 17 squared, and 8, 15, and 17 are primitive. So Samuel, the one that you've just come up with is not primitive because your numbers are divisible by 2. So we've got 3, and Kenza has come up with a 4th one. 7 squared plus 24 squared is 25 squared, because 49 plus 576 is 625, which is 25 squared. So that's really good. You've filled up the board. We've got 4 primitive Pythagorean triples. So then the question is, how many are there? Clearly, there's at least 4. So the question is, well, are there finitely many, like 100 or 1,000 of these things, or maybe just 4, or are there infinitely many? Well, the answer is there are infinitely many. Okay, so that's a theorem in number theory, which is a class that I teach. So how do you show that there are infinitely many? Well, the following formulas, this is a theorem in my course. The following formulas generate primitive, not just Pythagorean triples, but primitive Pythagorean triples. So A is m squared minus n squared, B is 2mn, and C is m squared plus n squared. So the question is, hold on, what's m and n? And the answer is, I haven't told you. Okay, so A, B, and C are going to be the 3 numbers that satisfy Pythagoras' theorem. Now, M and N are positive integers. Okay, we will assume that M is bigger than N. We will also assume that they are relatively prime, meaning there are no common factors other than 1. And we will assume that 1 is odd, 1 is even. So I'm putting quite a lot of restrictions on M and N, but assuming we stay within these guidelines, then these formulas, I claim, will generate Pythagorean triples. So let us see this in action. So I need to build a table with 5 columns. So M and N and A and B and C. Now, over to you guys again. Can you give me numbers M and N that satisfy all these conditions? So they've got to be positive. M's got to be bigger than N. They've got to be relatively prime, which means they don't have a common factor other than 1. And one of the numbers has got to be odd and one of the numbers has got to be even. Can you think of 2 numbers that satisfy all those conditions? I'll give you a second. 2 and 3, or 3 and 2, yes. So we had 3 and 2, 4 and 3 has been suggested. Do you want to suggest anything else? 9 and 13. Okay, wow. So let's go with those 3 pairs for M and N and see what I get. So I'm going to take these numbers and I'm going to put them into the formulas. So A is m squared minus n squared. Oh, yes, you're right, Moheen. I can't pick 13 and 9. They're both odd. So we're going to have to change one of them. Should we change the 9 to an 8? Let's go with that. Okay. So now these 3 pairs satisfy the conditions. So let's work with these 3. So 3 squared minus 2 squared is 5. 2 times 3 times 2 is 12. And 3 squared plus 2 squared is 13. And lo and behold, we've got one of the Pythagorean triples that you gave me before. And if we'd have started with 2 and 1, just to let you know, we'd have got 3, 4, and 5. So that's where the 3, 4, 5 Pythagorean triple comes from, is if you let m be 2 and n be 1. Now, someone chose 4 and 3. So let's plug 4 and 3 into here. 4 squared minus 3 squared is 7, because it's 16, take away 9. 2 times 4 times 3 is 24. And 16 plus 9 is 25. And that was another one on our list. So remember, we had 4 Pythagorean triples. I've accounted for 3 of them with these numbers here. Now this one, I'm guessing, is going to give me something that even I may have never seen before. Okay, so 13 squared take away 8 squared is 169 minus 64. So that's 105. Okay. 2 times 13 times 8. I think that's 208. Okay. And then 13 squared plus 8 squared is 169 plus 64 is 233. So no, I did not know this, but 105 squared plus 208 squared is 233 squared. You might want to verify that on a calculator, but I'm pretty sure it's true because it came from the formulas in the theorem. So then the only question remaining is, well, how does this prove that there are infinitely many? Well, the answer is you can pick m to be any number, 2 or bigger, and then just pick n to be 1 less. So I could have picked 13 and 12, and m would have been bigger than n. They would have been relatively prime, and of course 1 would have been odd and 1 would have been even. So you can always take a number here and then 1 less. And because there are infinitely many values for m, there are hence infinitely many Pythagorean triples that I can generate using these formulas. So, okay, so this one works, good. So that's pretty advanced stuff, but I think most of you understood that. And this is number theory, okay? This is, you saw it, number theory was part of the MSc 2020 list. So it is a branch of advanced mathematics. And that's what you do when you study mathematics as a major when you go to college, is you just look at all the different cool areas like number theory, and you just get introduced to them. And then if you like it and you're good at it, maybe you can keep on going and study it some more. And who knows, maybe one day you'll be the professor giving a talk just like this. Okay, so that is the end of my talk for this evening. I hope I've shown you a little bit about the world of mathematics. I am open to some questions. So Ryan says, is Pythagoras' theorem dependent on prime numbers? Well, I use prime numbers in a way to generate the triples, but there is a difference between being prime and relatively prime. So you can have numbers that are relatively prime that don't themselves have to be prime. So I'll let you think of that. 2 numbers that are relatively prime, they have nothing in common, but they're not prime themselves. Can you think of that? Can you give me 2 numbers that are not prime, but they're relatively prime? Well, 2 and 3 are prime. So yes, someone suggested 14 and 15. 9 and 8. Yeah, neither of these 2 numbers is prime, but as a pair, they are relatively prime. So there is a difference between prime numbers, which you just talk about one number being prime, And then relatively prime, you're talking about more than one number. Any other questions related to anything that I've talked about this evening? So Erica and Kai said, what makes a number relatively prime? Well, you have to have two numbers. And then, for example, these two numbers are relatively prime because the only number that divides into them is 1. There's nothing else that divides both 14 and 15. So they are said to be relatively prime. Any other questions I can answer about anything? Pythagoras, Armin, yes, he was Greek, yes. He lived, he's Pythagoras of Samos, I believe, and Samos is in Greece, and I think he was around about 580 BC is my best guess. Anything else? All right, well, it's been a pleasure talking to you this evening. I am going to leave you now, and I believe that Dr. Kwan will return.
Yeah, there is no other the plan after this. And so if you want to talk to each other, then you can remain and talk to each other and talk about yourself in the math and whatever the subject you want to talk about. Otherwise, you can type bye and leave. Tomorrow, we have another session, which will start at 2. And Dr. Brennan will talk about the mathematical journey as a mathematician. And so he will talk about his research area and what university professors are doing and what kind of interesting and exciting the research he's doing. And so you can ask any aspect of mathematician tomorrow. So I invite you to come tomorrow also. It will start at 2. Thank you, Dr. Griffiths.
Thank you. Have a good evening, everyone.
Yeah. As I said, type bye and your name. That'll be 2 o'clock with the same Zoom link.